Hey everyone, and welcome to This Explainer. Today, we're exploring one of the absolute most mind-bending shifts in all of human knowledge. We're breaking down Class 12 Physics, Chapter 11, The Dual Nature of Radiation and Matter. We're literally looking at the fundamental building blocks of reality. And trust me, it is way weirder and just far more fascinating than you might think. This shift in our understanding was so profound that it forced the entire scientific community to basically abandon everything we thought we knew, from classical physics giants like Isaac Newton and James Clerk Maxwell.
It sounds like a simple question, right? Is light a wave, just rippling continuously through space? Or is it a stream of discrete particles, kind of like a microscopic hail of bullets? Well, this core mystery completely baffled the greatest minds in physics for decades. Every single time they thought they finally had it figured out, the universe just threw them a massive curveball.
Okay, let's dive into this. Here is our roadmap for today. First, the photoelectric mystery. Second, Einstein's quantum solution. Third, work function and stopping potential. Fourth, the de Broglie hypothesis. Fifth, proving electrons are waves. And finally, number 6, wave-particle duality explained.
Starting off with Section 1, the photoelectric mystery.
To really grasp this mystery, we have to travel back to a time when classical physics thought it had the universe neatly wrapped up. Our timeline kicks off in 1887. Heinrich Hertz was running experiments with electromagnetic waves using a setup with sparking coils, but he noticed something incredibly strange. When he shined ultraviolet light onto his metal emitter plate, the high-voltage sparks jumped across the air gap much more easily. But think about that. Why would shining a light on a solid piece of metal somehow force free charged particles to just escape? This bizarre phenomenon, where light physically ejects electrons from metal, was dubbed the photoelectric effect, and it created a massive headache for classical physics.
So here's the exact problem they were facing. Classical wave theory predicted that light energy is a continuous wave. So logically, if you shine a really dim light on a piece of metal, the energy should just pool up over time until an electron finally gathers enough strength to pop out. Plus, classical physics said that the intensity, or the brightness, of the light should completely dictate the energy of those released electrons. But the experimental reality? It was entirely different. The emission was completely instant, zero time lag. And even crazier, a super bright, intense red light would never eject an electron, but a super dim, high-frequency ultraviolet light would eject them instantly. Classical physics was officially broken.
Which brings us to Section 2, Einstein's quantum solution.
Now, what's really interesting about this slide is that it took a true genius to look at a fundamentally broken system and realize that the rules themselves needed a rewrite. In 1905, Albert Einstein won his Nobel Prize by proposing a radically new picture of electromagnetic radiation. He hypothesized that light isn't a continuous wave just washing over the metal. Instead, light energy is built out of discrete, individual units.
He called these tiny units quanta of energy, what we now call photons. So think of light acting more like a hail of microscopic bullets rather than a continuous wave of water. The energy of each individual bullet or photon isn't determined by how bright the beam is, but purely by the light's frequency. The base equation is beautifully simple. Energy equals Planck's constant multiplied by frequency. But Einstein took it a step further to perfectly explain the photoelectric effect. He stated that the maximum kinetic energy of an ejected electron, Kmax, equals the energy of the incoming photon, h nu, minus the energy required to escape the metal, which is phi 0. This single math equation proved that high-frequency ultraviolet light means highly energetic photons, literally bullets packed with enough individual punch to knock an electron right out of its orbit.
Let's move into Section 3, work function and stopping potential.
You see, inside a metal, free electrons are held firmly in place by the attractive forces of positive ions. They can't just float away on their own. To pull an electron out, you have to give it a certain minimum amount of energy. This absolute threshold is called the work function of the metal, and we denote it with the Greek letter phi 0. We usually measure this in electron volts, which is just a super tiny unit of energy that perfectly fits the microscopic quantum world.
So, the crucial point is that you can think of the work function exactly like a toll booth. An electron has to pay this strict minimum toll to escape the metal surface. And how does it pay? Well, with the energy it absorbs from a single incoming photon. If a photon hits the electron but just doesn't have enough energy to cover that toll, the electron stays put. It honestly doesn't matter if a billion low-energy photons hit the metal. If none of them can individually afford the toll, absolutely zero electrons escape.
And just like in real life, the toll price changes depending on the neighborhood. Different metals hold on to their electrons with drastically different strengths. Platinum, for instance, has a really high work function of 5.65 electron volts. It's an incredibly expensive metal for an electron to escape from. Cesium, on the flip side, has a wonderfully cheap toll at just 2.14 electron volts, which makes it highly photosensitive and very eager to release its electrons.
And this brilliantly illustrates what happens next. Notice how the curves on the left show photoelectric current at different light intensities. See how they all beautifully converge on the negative x-axis at minus V0? That is the stopping potential. It's a reverse voltage applied to the collector plate that acts like a deliberate, forceful brake, stopping even the absolute fastest, most energetic emitted electrons from ever reaching the other side. This is crucial because it lets us mathematically measure the maximum kinetic energy of those escaping electrons. The fact that different intensities of light have the exact same stopping potential proves that cranking up the brightness just adds more photons. It doesn't add more energetic photons. And that graph on the right, it seals the deal. Maximum kinetic energy increases linearly with frequency, exactly as Einstein's equation predicted. Einstein hit the nail on the head. Light absolutely acts like a particle.
Which brings us to a massive pivot. Section 4, the de Broglie hypothesis. Because just as physicists were getting comfortable with the idea of light acting as a particle, it was time for the universe to get weird all over again. In 1924, a French physicist named Louis de Broglie asked a question that fundamentally shook physics to its core. If light, which we always thought of as a wave, can act like a particle, then can solid matter, which we always think of as particles, actually act like a wave?
De Broglie essentially theorized that absolutely everything in the universe has a wavelength. The formula he proposed was revolutionary. Wavelength, or lambda, equals Planck's constant divided by momentum. Now remember, momentum is simply an object's mass multiplied by its velocity. Because momentum is mass times velocity, a heavy object, moving at high speed, like a thrown baseball, has a momentum so unimaginably huge that the resulting wavelength becomes infinitesimally tiny. It's so unbelievably small we could never possibly detect it. But for an incredibly tiny light particle, like an electron, the mass is so amazingly small that the calculated wavelength lands right in the X-ray range, meaning it would be entirely measurable.
So, let's talk about the proof in Section 5, proving electrons are waves.
De Broglie's idea was a brilliant theory, sure, but science always demands hard proof. In 1927, scientists Davison and Germer built an experiment inside a vacuum chamber to test this seemingly impossible idea. Instead of using light, they practically fired a gun, an electron gun with a heated tungsten filament, shooting a continuous stream of actual physical electrons. They took this beam, accelerated it with high voltage, and blasted a solid target, specifically a nickel crystal. Then, they used a movable detector to measure the shrapnel, essentially sweeping around to see exactly where and at what angles those physical electrons bounced off the crystal lattice. Let's move to and see how this builds into their definitive, world-changing conclusion. Notice these specific peaks in the intensity data. If electrons were just physical pellets, they'd scatter completely randomly off the crystal, kind of like dropping a handful of marbles onto a bumpy, uneven floor. But that's not what happened at all. Instead, they formed specific, intense peaks of high and low intensity at very certain angles. This is a diffraction pattern. Think of ripples of water passing through a slit and interacting with each other, creating crests and troughs. Diffraction is a property absolutely exclusive to waves. The atomic spacing of the nickel crystal was acting exactly like a diffraction grating. The real eureka moment came when a 54-volt beam produced a massive peak exactly at a 50-degree scattering angle. With that single peak, Davison and Germer had just caught solid matter acting as a wave.
Wrapping things up in Section 6, wave-particle duality explained.
So, the ultimate takeaway from this chapter is that nature simply refuses to be put into neat little classical boxes. When we look at the photoelectric effect, we see undeniably that light behaves as discrete particles or photons. But when we look at the Davison-Germer experiment, we see undeniably that physical matter, like electrons, behaves as waves. The truth is, at the microscopic quantum level, it's not either-or, it is both. The universe operates on a fundamental, incredible wave-particle duality.
The realization that matter itself has a wavelength birthed modern quantum mechanics, leading to everything from electron microscopes to the tiny chips powering our smartphones today. But it leaves us with a lingering, totally fascinating question. In a quantum universe that refuses to choose between being a wave and a particle, what else is classical physics hiding from us? Keep questioning, keep learning, and thank you so much for joining me for this explainer.